Welcome to the second last talk of today. I guess you already had a lot of input today, and I'm sorry to add another pile on top of that right now. So what? Okay, I try to make that bearable. I'm not sure if I succeed. Anyway, my name is Uwe Friedrichsen, and I work for a quite cool company named Codecentric. That cool should be enough of advertisement for the company, so let's leave that aside. My history, working computer science, IT meanwhile, more than 30 years. Did a lot of nice things, did a lot of not so nice things, did some ugly things. So basically the same experience that probably you have, maybe some other details, but let's skip that because usually that's a 90 minutes talk and I have 60 minutes. So again, sorry about that. Therefore, I have to leave out a few bits and pieces. But anyway, let's start up. Resilience. I mean, I'm around for quite a while and talking about resilience as I'm quite heavily involved with distributed scalable systems, and resilience is a very important topic in there. But at least when I started up, and also sometimes right now, I still get reactions like that. So like, huh? What that? And then every reasonable person looks it up then, and okay, we look into a dictionary. It's a bit odd. I didn't take Wikipedia, sorry for that, but anyway. So I took a real dictionary. And so resilience, the definition here is so that I can return to the original form from being bent or something, like a spring that you bend around and let loose, and then the boing, it goes back to the original position, or recover readily from illness and so on. And yeah, it sounds nice, but again, I mean, we're in IT, aren't we? So has that got to do with IT? So what's it all about? And then I say, okay, I try a little bit better explanation, and then I usually start up if I talk about resilience. First thing you have to know, it's all about production. And before you go to the third, give me a second to explain that. So what I mean with it's all about production is we're building software to create some kind of business value. So making money, satisfying customers, best both of it. And we only create that business value with software involved in production. Therefore, it's all about production. And having software in production isn't enough either, because your system needs to be up and running. Available is the official term for that. Availability is important, because as long as your software isn't doing what it's intended to do, so it's down or doing the wrong things, it doesn't deliver any business value. And that's why you wrote the software in the first place. So it's all about production, it's all about availability. So let's have a little bit deeper look into that availability thing. Here's the formula for availability. I picked a quite easy one, so even for the fourth day in the afternoon, that's almost understandable. So it takes me 5 minutes, so you're probably faster. The definition, there are several definitions around for availability. I like that one most, actually. I took that from Robert Hanmer's book, Patterns for Fault-Tolerant Software Design. So it's defined, on top you have mean time to failure, which is the average time from a system coming up until the first failure is seen from the outside. And on the bottom line, so in the denominator, you have the sum of mean time to failure plus mean time to recovery, so that average time from when you see a failure until the system's back up. So in the denominator, you have all the time, and the fraction of time where everything works as designed, you have in the numerator. So quite straightforward, and you try to maximize that towards 1. So becoming as close to 1 as possible, or if you like percentages more, you multiply all that stuff with 100, and then you have your 99% availability, 99.9%, and all that stuff. Last thing to note here is, if we talk about failure, There are several kinds of failures. It's not only crash failure, what most people think about when they talk about failure or think about failure. So systems up and boom, it's down and it's gone. That's the easiest way. We also have omission failures when systems become brittle, sort of. So yeah, sometimes responds, sometimes does not, and so on. And then we have the timing failures, which is that system responds, but too late. So I can't wait for that long. Or response failure. So it responds, but unfortunately the wrong thing. And especially in distributed systems, that happens quite often. So if we think about replication, eventual consistency, and all that stuff, these are response failures also. It's not only software bugs. And then we have the very mean ones that we're not going to talk about today. It's the Byzantine failure. So when the system goes berserk, basically. So it does whatever it wants to do, and you have no clue what's the heck's going on there. So these are all kinds of failures, and we have to deal with all of them. So that's when we talk about availability. Whenever something goes wrong, it becomes slow, it becomes brittle, it crashes, it gives you the wrong answers, all failures. That's important to understand. So it doesn't help to have a system which is up all the time and always gives you the wrong answers. That's not availability. So core question is, how can I maximize that? Because we want to generate business value. And for the guys in here who are quicker than I am with math, you immediately see, okay, the secret here is to make mean time to failure a lot bigger than mean time to recovery. So that mean time to recovery becomes irrelevant relatively to mean time to failure, and then you're getting closer to 1. Okay, and of course there are two approaches for that. The traditional one is I try to maximize mean time to failure. So I try to maximize the time until a failure becomes visible or happens at all. And that was quite a good idea in the past, and most of failure engineering we see around there in the past goes for maximizing mean time to failure. So we take big, high availability solutions, cluster solutions, redundancy is a redundant network, and mostly infrastructure, redundant infrastructure, because that was the biggest source of failures we had on these systems, and then a lot of extensive testing additionally. So because mostly the systems were running in isolation mostly, and so not a lot of interconnection and so on, and there was a perfect approach for that, this kind of trying to think about what can go wrong and then already take measures in advance to prevent that. So if that was perfectly fine, so what's the problem right now? In simple words, today, basically every system is a distributed system. So even if you sit in a normal telecommunication company and you have a CRM system, it usually talks to about 50 or 100 different systems online. Or if you have a claim system in an insurance company, it also talks to 30 other systems, and so on. And all these systems talk to each other and online. And if one system goes down, the others quite often have a problem. So the world today is distributed, basically. And if you talk about distributed systems, you can also have a quick look at the 8 fallacies of distributed computing by Peter Deutsch. Terms like the network is reliable, not. Latency is 0, bandwidth is infinite. It's all fallacies. So there are many, many sources alone in the network which can give you failures. And we haven't talked about application level yet. And this leads Leslie Lamport, one of the gurus of distributed systems, to his quite sloppy definition. Distributed system is one in which failure of a computer you didn't even know existed can render your own computer unusable. So what can we learn from that? Failures in today's complex, distributed, and highly interconnected systems are not the exception anymore. They are a normal case, and they are not predictable up front. And, sorry about that, it's even getting worse. So if we talk about cloud-based systems, I mean, the cloud provisioning, resource provisioning model is so much superior to the traditional provisioning model that it will eventually blast away the traditional resource provisioning model. I mean, I want to have a resource, I do it via self-service API, and here it is. So no longer waiting for 3 months for a test server or anything like that, or scaling up and down in production, all that stuff. But to the price of a lower availability of the resources than you usually have in a high availability solution. Or you talk about microservices distributed by default, even more moving parts. And at the same time, we get ever increasing availability requirements. So zero downtime is the word du jour at the moment. And you have to solve that problem while your system becomes more and more distributed and gets more and more moving parts. And then also IoT and mobile, it comes into play. So you have even more not so reliable peers in your system talking over quite unreliable network connections. Or social media, so completely unpredictable load patterns. At the moment, your server is idle. The next moment, it gets just flooded with requests, and you have no idea where the heck they're coming from, and so on. So moral of the story is we are not going to go back to the good old times. So we are facing a never-increasing complexity and connectivity in our system landscapes, which leads to the mantra of resilient software design. Do not try to avoid failures, embrace them. Accept that they will happen all the time and deal with that. Which brings us to resilience approach for maximizing availability. If I accept that I cannot really maximize mean time to failure, that there are way too many sources of things that can go wrong, my only chance to maximize availability is to minimize mean time to recovery. So to take measures that if something goes wrong, I can recover very quickly from that, or at least that I can mitigate the problem in a way that the user isn't experiencing it or gets at least a degraded service which he still can live with, which the user still can live with. Which leads to a quite different definition that I usually use if I define resilient software design or resilience in terms of IT. So for me, resilience in IT terms is the ability of the system to handle unexpected situations without the user noticing it in the best case and with a graceful degradation of service in the worst case. Okay, now we've seen what resilient software design is, why we need it, and what's the difference to traditional stability approaches. But we're all developers, engineers, so our main question is not what and why, our main question is how. So how can we build that? And that's quite a broad topic, actually. So I'm currently developing sort of a pattern language for resilient software design. I'm actually doing that for 1.5 years in my non-existing spare time. And it's getting broader and broader and broader, and I figure out there's quite a lot to learn, and it's way much more than we could do in the remaining 40 minutes that we have here. So what I decided to do is I give you a starting point in here in the remaining minutes. That's a small pattern language. It's still 20 patterns, but I have to skip some because, as I said before, it's usually 90 minutes talk, and I'm probably quite sure that the next speaker will be quite upset if I'm going to talk 90 minutes here and will drag me out somehow. So we're not trying to do that. And so I have to skip a few patterns in here, and I basically stay at the design level. I have some code examples in some places, but I won't be able to go down to every detail. And I picked isolation as a starting point, because usually when you think about resilient software design, we usually start to design your solution is that you think about isolation, and then you start to add the other parts. And that's what I'm going to do here. So I start with isolation, which is more like a principle here in the terms of that presentation. Principle is a higher level topic where the patterns are organized around. What's isolation? I mean, the idea is that the system must not fail as a whole. So what you're doing is then you try to split up your system in several parts and try to isolate them against each other. So if one part of the system fails, the other parts of the system must not be affected by that. So we try to avoid so-called cascading failure. Something goes wrong here, and this drags that one down, and that one down, and that one down, and now we have a perfect catastrophe, and we don't want to have that. The system as a whole must stay available. And there are several patterns around. I've got two here. First one is bulkheads, probably quite a well-known one. So it's actually the core isolation pattern, and it's usually where all efforts to build resilient systems start. You try to figure out these bulkheads or failure units or units of mitigation. There are several terms for that. And because they are the basis for redundancy and for all other approaches to build resilience into your system. And also how to build scalability in your system, which is more or less scalability is nothing but sort of success resilience. Because if your system becomes successful, more customers come to that, you have to cope with that. It also can be an unexpected situation. So the bad part of the story is it's a pure design issue. So for all these of you who like these flaps here, I'm an architect. If there's still anyone around here who likes being an architect, you're quite often talking about separation of concerns, and this is another concern. So this is another aspect that we have to have in mind when we think about how to split our system best, our system at runtime here. So if you're talking about microservices, microservices are a perfect candidate for being a bulkhead. Not necessarily all the time, but quite often you have, if you think about resilience and microservices, you think about how to slice them in some way that they also become resilient, or that you can isolate them quite well against the rest of the world, and that it still makes sense in terms of design. Again, pure brain power, no frameworks here or anything that really gives us out of the box. I mean, even if you go for ACA or something like some great framework that are out there, they say, here's an actor, but this thing isn't resilient in itself, and I never tell you what needs to go in there. You have to think on your own which part of the functionality goes in there. Okay, the next one, complete parameter checking. I mean, you might think, what's the story in here? The problem is, we all know that. And I'm not sure about you, but I've hardly seen ever a system which really implemented that. We all know we should check all the parameters on our boundaries, and hardly anybody does. So, yeah, we have to do that if we want to have resilience. We have to protect ourselves from broken or malicious calls which come in, and also from broken or malicious return values which come back up from downstream calls. So I've seen so many null pointer exceptions from people just blindly using the results from their query to the database that I can't count them anymore. And I never understood that actually, because for me the definition of a production database is that it's broken in some way, that it has inconsistent records in there. Every database that only has consistent records in there is a test database usually. I've never seen a production database which was perfectly consistent. It happens. It's real life. And so I have these tons of null pointer exceptions, and even more, and also having too many, broken calls coming in. Still pay attention to Postel's law in there, so don't become an interface Nazi. In a way, so the idea from John Postel, he's an internet pioneer. He wrote the original RFC for TCP, and what became famous as Postel's law was his idea. What he said: be conservative in what you do, be liberal in what you accept from others. So, if I talk to someone else, I try to stick to the specification. But if somebody else talks to me, If it still makes sense, I'm going to accept that. There's an extra parameter, so what? I'm going to ignore that. It's not exactly the format, but I understand that it's okay enough, and so on. As long as it makes sense to me, I accept it and try to process it. If it doesn't make any sense, I reject it. And that gives us a lot more robust systems in the end. I will skip the part about the specific data types. So let's move on to loose coupling. Loose coupling is another principle which complements isolation. By trying to reduce the coupling between failure units, again, reducing the risk of cascading failures. So less coupling between the pieces, fewer chances that one system or one piece is going to tear down another one. Quite well known in this area is the idea of asynchronous communication, which decouples the sender from the receiver. I mean, the problem that you usually have with synchronous communication is the moment you do the synchronous call and the other part the resource you call doesn't respond, you stand still and you can't you don't have the control because you're waiting for the response. So you're you don't have the control anymore. So you can't take any alternative actions and anything like that. And asynchronous communication relieves you from that problem because I send out the request and I get back the control. So I can still react to timeouts and other problems and so on, or to crashed machines on the other side. I can still respond to all of that. And therefore, it's quite useful to break these cascading failure chains that you quite often get with synchronous communication. And problem in here is that quite often hear then, whoa, that's so hard. This asynchronous communication stuff is so much harder than synchronous communication. Do we really have to do that? And my answer is, you're only halfway right. Because yes, it breaks the call stack paradigm. The call stack paradigm is nice in the way that it works the same way as our brain works, so in a linear fashion. So A calls B, B calls C, C comes back, B calls D, and so on. It's perfect the way like our brains work, not internally, but the way we think. Asynchronous communication is actually how the brain is wired internally, but we can't understand how our brain is wired with a conscious part of our brain. It's quite interesting if you think about that for a while, but that's a different story. And so we quite often have quite a hard time to reason about these communication networks as asynchronous ones. That's true. On the other hand, from the technical point of view, if you go for synchronous communication and you want to get resilient, you have to build in some kind of timeout management, which I'm going to show later. And then you have the problem, I do a call, and I wait till the timeout happens. So if the timeout doesn't happen, so if I get the answer back before the timeout happens, everything's nice. But once in a while, it will strike. And now I've got the problem, I have no idea what's going on, because didn't the call reach my downstream resource, or did it reach the downstream resource but broke while being processed, or did it reach the downstream resource and is still processing, but actually everything's fine, it will just eventually complete in a second later or something, or did just the return message doesn't come back. So what the heck am I supposed to do? Can I call it again, or doesn't it make any sense to call it again, and what's my measure, and so on. And just after a moment, synchronous calls are as complicated as asynchronous calls. The only difference is that in asynchronous communication, it can happen to you that might become harder for you to reason about the whole network. That's everything. So the difference is not, is it more complicated or less complicated? It basically, again, for the architects and designers in here, it gives you quite different designs, because synchronous calls usually give you a top-down slicing of a system, and asynchronous calls usually give you a left-to-right slicing of the system. You end up with quite different designs, which is a way more interesting point than if is one thing more complicated than the other one, by the way. Okay, long enough. So let's keep the location transparency as a pattern short. I mean, yeah, if I only have to deal with a logical name and don't need to know exactly where in the system this other resource lives, yeah, makes things easier if I think about redundancy, failover, scalability, and so on. So let's keep that short and move on to event-driven communication. So event-driven is one flavor of asynchronous communication. The other big flavor is usually the message-driven communication. So message-driven is A calls B. Event-driven is basically I do something, I send out an event, and I don't care anymore. So whoever wants to know about that and is interested in that can subscribe to me. So basically it reverses the dependency, so the location dependency, because sender does no longer need to know where the receiver is, but the other way around, which is quite interesting in some places when you set up your designs. And if you've got a broker in the middle, you can achieve full location transparency. Again, as I said before, a very different approach to normal request-response paradigm. Just to show them a picture, so sender, receiver with request response, you have the typical dependencies. Sender needs to know where the receiver is. Event-driven without a broker, it turns the dependency the other way around. Receiver has to know where the sender is. And the last one, with a broker, it's completely decoupled. Again, design issue, and as with all things in design, no solution is better than the other. They just have different trade-offs. So, like in Indiana Jones 3, choose wisely. Another pattern in here is, and I want to mention, it's from a different domain, but it blends in quite nicely. Here is statelessness, because it's quite important in the domain of resilient software design. So it supports location transparency, but it also supports a lot of other things like scalability, like failover, and so on, because it's quite hard to relocate a service from a broken node to another node if there's state, because first of all, you have to move the state. And also failover is quite hard because you have to replicate the state in some way. And scalability is hard because you have to replicate the state across all the nodes, and it gives you a hard time if you ever tried to replicate, not in an eventual consistent, but even in an eventual consistent way, if you try to replicate a state, and if you ever tried that before with more than 5 nodes or something, you know what you're talking about. So it's a very important pattern, and usually the rule of thumb is avoid state in your services and in your units. Try to move the state either to the top, so to the client side, or to the bottom, so to the persistent layer. And try to keep the middle part stateless as much as possible. Oh yeah, my perfect enemy, relaxed temporal constraints. Problem is that I could talk about that one for 90 minutes alone, and I actually talks about that one for 90 minutes alone. So I try to keep that one short. Problem is that strict consistency requires a really tight coupling of the involved nodes. What do I mean with that? Strict consistency means that whenever you ask a request from the outside, and no matter which node you're asking, you always get the same answer. So and that means these kind of asset transactions, so these asset properties that you have this atomic updates things and so on, and this serializability or even linearizability and so on, all these properties that you need. And problem is then you have to implement a really tight coupling between the involved nodes which replicate their state in you're talking about. And so if one node goes down, usually all the availability of the other nodes are compromised, and all that stuff gives you a lot of headaches. And if anybody of you ever tried to ever worked with XA protocols, so with these two-phase commit protocols, you know what I'm talking about. They are just a pain in the neck. And so basically, if you want to build highly available systems, which are distributed, then you usually get to loosen the consistency level, so to lower the consistency level to get better availability. It's also what the CAP theory basically tells you. So partition tolerance isn't an option, so you have to be able to deal with partitioning of your system, and you must be able to do reconciliation if it comes back up and all that stuff, because otherwise you are per default inconsistent, which isn't an option. And so you have to get these trade-offs between availability and consistency. So CAP, that's basically in here. And there are a lot of discussions around here. Oh, we need that ACID transactions in here in our systems. That's so important. It's a business requirement that all our transactions are ACID all the time, and eventual consistency isn't an option at all. And that's where I usually contradict, because I say there isn't any single business requirement for ACID transactions, because the real world isn't ACID. In the real world, out here, a concept like ACID doesn't exist. In the best case, the real world is eventually consistent. In the normal case, it's simply inconsistent. So there can't be a business requirement for that. And then the people usually come up and say, yeah, but if you have this bank account example, so I transfer, so here money transfer from one account to the other one, I need an ACID transaction. I say, why? I mean, I tell you how money transfer in the real world works. I transfer some money from my account to your account. What's going to happen in the real world? The money from my account is gone. On your account, nothing happens. And then, depending on the banks involved, so a day later, 2 days later, eventually the money shows up. So where is the real-world requirement for ACID transactions? So don't get me wrong, there's a big case for ACID transaction, but it's a programming model. It's not the business requirement. The programming model is so much easier because you don't have to deal with all these intermediate, temporarily inconsistent states. Gives you a big relief when you have to reason about those systems. So programming in eventually consistent environments is really, really hard. So if you have a chance to go for ACID transaction, do it for your own sake, not for business requirements. That's the part of the story here. Let's briefly mention idempotency, because also a very fundamental pattern here. Idempotency, the basic idea of idempotency is that you can do call several times without getting different results or different side effects. So it's a very simple example. You have a counter and you have a function or an operation like increase. Calling increase several times is not, increase is not idempotent, because it makes a difference if you call increase 1 time or 2 times or 3 times. If you have another action, so another operation like set, you can call set to 5, 1 time, 2 times, 3 times, or 100 times. The result will always be the same. So set is idempotent. Increase is not idempotent. And in distributed scalable systems, so if you want to build resilient systems, it's very hard to deal with non-idempotent calls, because, as I said before, you call something, it doesn't respond, and now you have to figure out what's going on. Can I send this write request again, or is it just still processing, or is something else broken in here, or do I just have a network partition? And all at once, I have to get a tight coupling with this other peer, the resource I just want to call, and I want to have a loose coupling with, but I need a tight coupling because I have to figure out the internal state of that. No fun. So no good idea. And so usually what I'm going to do is I try to implement these action, this write request, in an idempotent fashion. So if it goes wrong, it's quite easy to solve that problem. I just go on and I just wait for a moment, and then I retry. and maybe I call some supervisor or something, and then I retry again, and yeah, it's a lot easier, and I still keep my loose coupling. Therefore, idempotency makes it quite easy. Idempotency also makes it easy for me to get exactly one semantics implemented, because what I usually do in distributed systems to implement exactly one semantics, which I quite often want to achieve, is I take an at least once communication channel, which gives me at least once semantics, so it delivers messages once or more times, but at least once. And then I implement idempotent actions on top of that, because if it's delivered more than one time, it doesn't matter. So in the end, I end up with exactly one semantics. Also, very important pattern in here. I also had, I have a slide in here which I want to skip, how I get a unique request token. You can look at that up in the slides later on. The idea basically is I have a known idempotent call. I want to make it idempotent. I decorate that with a unique request token, which I evaluate on the server side, and so on the resource side. If I've seen that token already, then I'm not going to process it, and otherwise I'm going to process this request. And so you can more or less, with a little bit of wrapping of your resource and your calls, you can turn non-idempotent calls, idempotent calls into idempotent calls, basically. Okay, let's also, where are we? Yes, here, skip that one. And move on to latency control. So, latency control, another principle which complements isolation, and it helps you to detect non-timely responses, basically, and also so in this way to avoid a special class of failures, timing failures or temporal failures. And the best known pattern in here is probably timeouts, which is quite straightforward from the basic idea. I mean, as I said before, we want to preserve our responsiveness. And if I do a synchronous call, what I have to do is then I have to spawn that call in a different thread or however, and then to keep an eye on the response time. And if it takes too long, when timeout happens, I stop waiting, I discard the call, and take an alternative action. That's basically the idea in here. And this alternative action is also known as fallback, and is basically where all these correction and mitigation patterns and all that stuff blends in then usually. And quite often, people think, oh, that's quite hard to implement, but basically it's very straightforward, especially in Java, to implement timeouts with standard library means. So it's just 3 more lines of code, even without taking big new libraries or anything like that. I've got that example over here. So I'm not sure if this mouse works somewhere. Yeah. Is it also seen here? Yeah, cool. So I have to look over here. So basically what I'm going to do is I'm wrapping my action, which is blocking, in a callable. And then I just create a single thread executor, and I submit that. And then, and that's basically all, because what I've got then is I get back a future with template parameter of my return value. And down here, and future has 2 methods in there. It has a blocking get, don't use that one, and it has a one which is also blocking, but with a timeout that I can add to that. And after the timeout, so if everything works fine, I end up here in the next line, and I can simply process the result of the request, and otherwise I get a timeout exception. And then I can take my fallback, my alternative actions in here. The rest is standard stuff, so a little bit of Java fancy around then. But question is, why aren't we always using that one? And the answer is not because we are too lazy, but because we have no freaking clue what to implement in this piece of code. So what the heck do I have to implement here at this place? Because usually you get your requirements and you try to best to implement your stuff, and nobody told you, or at least there's even no strategy, no nothing what to do if I have a technical problem. So you go back to your product owner and ask, hey, what am meant to do here? And here you have to make sure that this must not happen. It's your job to make sure that it's not going to happen. And then you say, okay, I just put a comment in here, this is not going to happen, set, and so on. And then we're waiting until it happens the first time, because it will happen, it can happen, so it will happen. And when the call center is flooded by angry customers because the system is not responding anymore, we're going to discuss it then later. And okay, be a little bit more diplomatic, basically. But quite often these folks then realize it's important to think about that. So no matter if they're architects or project owners or product owners, or if they're requirements engineers and so on, you have to have an answer how to respond to technical failures. And it's a business answer, because it's a difference if it's just okay to show a web slide, just show a web page, come back later, or if this action is so critical that you want to implement, for instance, if your database is down, a secondary queuing system where you queue your requests and process them later on when the database is back, because you're losing sales, for instance, or anything like that. So you can't decide that on your own. It's very important and very fundamental that these kind of questions are discussed with somebody who knows about the business demands and requirements. Okay, the big brother of the timeout is a circuit breaker, probably the most or the best known pattern in resilient software design. Michael Nygaard wrote quite a brilliant book, Release It, in 2007. Still very, very important to read right now. And he also mentions a circuit breaker. The core idea here is if you know you're going to fail, you better fail fast, which is some basic principle of resilient software design and fault-tolerant software design. So if you know that you have hit a timeout by calling resource several times, you don't need to do that more over and over and over again. So you put some kind of guard or some kind of gatekeeper in front of the call. So that's the circuit breaker, actually. And if it always watches the requests and responses. And if you have problems with that resource, or it doesn't answer, or it's slow all the time, and like, so after a while, the circuit breaker simply trips, and all subsequent calls, they get the response, don't try it at the moment, there's a problem over here, so come back later. And then after a little while, it lets one additional request going through and observe that, oh, still too slow, okay, we're waiting for another while, coming back later, and then now it responds nicely again, so let's open the connection up again. That's basically the concept of a circuit breaker. You can also use that for different kinds of failures, but most often it's used for crash failures and timeout failures. You can also implement that on your own. It's not too hard, but it's a little bit more of effort than the timeout I've shown before. Usually what I recommend in here is that you use something like Hystrix. It's a very well tested and battle-tested library from Netflix. They're using that in their resilience engineering. And it basically revolves, so it gives you some features, and it builds all around kind of a circuit breaker. It also has bounded queues in there, sort of load shadows. They also provide you with timeout management and several other patterns, but basically it all works around or builds up on a quite sophisticated circuit breaker implementation. And just to give you an idea how that feels, very rough idea. Here's a little example. I have to find my cursor again. Here it is. Okay. Hystrix builds on the command pattern. So everything you implement in Hystrix derives from the Hystrix command. So all your calls that you want to protect or to guard with a circuit breaker, you have then to write your own command, which is derived from the Hystrix command. The template parameter is return value, basically. And then when you want to pass in some parameters, some request parameters, what you usually want to do, you do that as a constructor parameter. So one request call is one instance of the command. So no reuse or something like that intended in here. So they hope for a good garbage collector, basically. And you save that, and then you have to override the run method. That's basically it. And usually in here would be the real call to your downstream resource that you want to guard. I simply put a hello world in here. So that's all. And return that. And that's basically it. There's another function method that you can override. That's the get fallback method. This is always called whenever this run method takes too long or fails in some other way, then the get fallback method is called, and then you can put all this advanced error handling in there. And usage, on the other hand, is also quite straightforward. You instantiate that, put in your parameters as constructor parameter, and then you simply call execute. That's the synchronous way. And then it runs, and if it hits timeout, it comes back and tries to call the get call. And so it's quite straightforward. Also gives you asynchronous variation. It gives you an RX Java implementation on that. Basically, internally, it's very much implemented on the reactive pattern. But it's quite straightforward to use the first time. So it's no magic. There's still a kind of a learning curve, especially if you want to fine-tune that in production. But from a developer's point of view, it's quite straightforward to use that. And that's what I would try to encourage you if you never thought about building things like a circuit breaker in your design. Have a look into that one. I mean, it gives you a lot more than just what you see in here, because it gives you a full-blown circuit breaker implementation where it also checks for queues, it can implement back pressure, and all that stuff. It's all in there. So I'm not going to get into any details of that picture, which I've taken from the documentation from Hystrix. So if you want to dive into resilience, have a look at that. Let's skip the fail fast. I mean, the basic ideas I talked about already, and let's talk for a second about fan out and quickest one wins, because or quickest reply, because that's a very different way to deal with latency management, and I just want to show that one because to give you an idea, there are very, very different ways that we usually don't think about in the first moment. So you want to keep latency low, and the idea is then that you say, I'm not calling one downstream resource, I'm calling several of them, so I have multiple resources now. I send out my request to all of them and wait just for the quickest response, because one service, one resource sometimes gets slow, garbage collection, whatever, network hiccup, anything like that. Several, the probability is way is a way lot smaller that this is going to happen, and therefore it's a very nice tactic to deal with those issues. Because one thing needs to be clear, if we talk about distributed systems, we only talk about probabilities. So all this determinism that we use from in-process programming is gone there. So we just lower the probability that we get latency. We don't have any guarantees about that. That's all of that stuff is about probabilities. And what's quite interesting in here is, so you have a trade-off between waste of resources and latency. So you trade resources, added resources for lower latency, and that's typical design decision that you have to make. And So some guys from Google, Dean and Barroso, wrote quite famous article, Tail at Scale, where they played with all that, and by implementing something that you call backup requests, so sending the second request a little bit later, so not immediately sending out the request to several resources, but just sending it out to one resource and then a little bit later to the other one, they were able to get the overhead, so this additional resource consumption down to an overhead of 5%. By giving up a little bit of optimized response time because of that delayed call. So there's a very different way to deal with latency. Let's skip the bounded queues, or just a very short word about bounded queues. Quite often we are used to thinking in unbounded queues. We must not lose any requests, but unbounded queues are the enemy of latency. So because the longer your queue gets, the longer it takes until your request gets processed, especially if the resource is already heavily loaded. So you better go for bounded queues and watch them tightly. And if the queue is full, you simply do not accept any requests anymore from your senders. And so that's what's called back pressure. So it has to wait until the resource is available again. That's very much better than letting the queue grow and grow and grow, because then your timing problems are going to grow and grow and grow. Have an example in here how to implement that on front of the on front of a executor service, but I'm not going to into that. Only thing you need to know is whenever you try to instantiate an executor service from the executors, the static class, you always get unbounded queues. So if you want to have a bounded queue in front of that, you always have to instantiate that stuff explicitly, and then you can also even implement your back pressure strategy and all that stuff. All that stuff's built into the standard library. You just have to use it. Let's skip the load shatter and go to the last principle, which is supervision. Why is supervision important here? What we've seen up to now, loose isolation complemented by loose coupling and latency control helps us to build bulkheads or failure units, let's call them building blocks, which are quite well isolated against cascading failures from the outside. But my goal is that the service as a whole stays alive and will keep on running. So just protecting me from other services or other units of failure units having problems isn't sufficient. Because in the worst case, what's going to happen is, hey, I run perfectly, and then you see going the lights out one by one until you're the last survivor, and but the service doesn't work anymore then. So you need some other kind of level which supervises the service as a whole, and if one service has a problem, yes, the other ones are not affected by that, but this must be repaired. So this self-healing properties of the system, and therefore you need that supervision part. So detecting failure units and also providing a means to send redirect problems to. What I mean with that, I'll show you next slides. So typical pattern is monitor, quite well known. The only thing which is very important to understand in here is it's no longer sufficient to send out an email to your administrator whenever you see a failure or a problem in your system, because there are always problems in your system. So don't drive your admins to a burnout. Build in self-healing properties into your system, which is very important. The rest is up to you. And let's skip that one and go to the last one, which is escalation, which I want to. That's where I come back to a thing I mentioned before. Quite often inside a unit, we don't have enough information or time, or both, to handle a problem that we just observed. So we either need more time or more information. And as we can't handle that problem locally, we need an escalation peer. So I say, I've got a problem, please help me. And so we quite often end up in multi-level hierarchies, which is basically design issues. So if you have your control and data flow here on the lower level, you get an orthogonal flow for control and error handling. Quite important for all those people who are used to working with single process systems, because what we're usually doing there also with request response pattern, I've got a problem down here, so I just throw an exception and it goes back up. Okay, and then it's locked and we forget about that. No, we're doing some proper exception handling, but it's not an option in a distributed system to tell your caller what your problem is. So that's definitely no option for you, because your caller will just tell you, and what should I do about that? I have no clue about that, what's inside of you. I just wanted to know, I just had this request and I want an answer. So just tell me, do I get the answer? Won't I get the answer? Or does it make sense to come back later? Whatever, but I don't want to know anything about your stack trace and all this additional error information. So you need something else where you put that. And this part, the supervisor is going to handle, is meant to handle these kinds of problems. Your caller just should get back the response, or simply information, you won't get any response here at the moment. So the 503 in HTTP, come back later, or don't come back, I'm going to die because my supervisor is going to take care about that. So that's this language built around isolation and a bit of supervision. As I said before, there's a lot more that I unfortunately don't have the time to talk about. There are all these recovery and mitigation patterns. What options do I have if I encounter a problem, no matter if I handle it myself or on a supervisor level? There are more ways to supervise your system than just this one strategy. There are a lot of architectural patterns around. There are anti-fragility patterns around, which helps to make the system even more robust against problems. So anti-fragility is nothing new in the resilience domain. That's 20 years old, this idea. And then, of course, fault treatments and fault prevention patterns. So some kind of upfront nourishing of the system to reduce the likelihood that something bad is going to happen, not get rid of it. So, as I said, it's a rich pattern family, and quite a lot that you can dive into. Yet I think with this starting point, isolation, you have a good foundation to spread out into the domain of resilient software design. So let's wrap up. As we've seen in the beginning, today's system landscapes are distributed and it's getting worse. So failures in today's system landscape are the normal case, and they're not predictable and they're not avoidable at all. So what we need some kind of resilient software design from scratch. We have to think about how to make our systems, to design our systems in a way that they become robust. It's a very rich pattern language, and you can spend a lot of time in there. But still, isolation, as I showed you with all these concepts around here, is a very good starting point, and then you blend the rest of it into it, basically. And if all of that has been way too much, as again I say sorry that it's so short time for so much information, and you just gave up somewhere in the middle and just want to take away one sentence from the whole talk, then take away this one sentence. Do not try to avoid failures, embrace them. That's what I had for you. So first of all, thanks a lot for your time, for your patience, and have a great conference. Thanks. I would suggest if there are any questions, just come along, ask me, or anyway later, because next one is probably waiting to get on stage here.